Today we're going to look at another way of finding volume with calculus called the cylindrical shells method. So this first example we have here, we're going to try to find this volume by taking this area right here bounded by this function and this function. So you can see here, and the y equals 0 is the x-axis. And we're going to rotate it around the y-axis over here in order to get a 3D shape and find that volume. Well, if we use that disk washer method we've used previously, what we would do is like take one function here minus the other function here and rotate it around. We could do that, but the problem with this one is it's just one function. We can't subtract the same function, so the disk washer method would have a hard time working on this problem. So what we're going to do instead here is we're going to try to use another shape we have in geometry, and we're going to think of, well, what if we take like part of this? What if I took kind of a representative cut of this and rotated it around? And if you do that, what you would get is a shape that you've seen before. It'd have three-dimensional to it, and it'd kind of be this like hollowed out cylinder that we would want to try to find the volume of. So how do we find the volume of a hollowed out cylinder is what we're going to look at next. Well, this cylinder would have kind of an inside radius right here, and it would have an outside radius to the outer part of that. It would also have some kind of height here as well. And so what we're going to do is we're going to find the volume of both that inside cylinder and the outside cylinder. If we subtracted the volume of the hollowed out cylinder, we would get the volume of the remaining stuff there. And how you find volume of a cylinder is pi r squared times the height. So we got the outer one having this r2 radius, that's what we got right here, and we got the inside radius with this r1 radius, that would be right here. If we subtract those, we should be left with this volume. Well, we're going to do some math stuff with this to come up with something new. So first thing we're going to do, because we have both pi and h here, we're going to factor that out. So if we factored out the pi and the h, we would be left with r of 2 squared minus r of 1 squared. That's a difference of squares. Just like if I had x squared minus 9, that's factorable into x plus 3 and x minus 3 because it's a difference of squares. So we're going to use that same trick now here. So if we factor that into a difference of squares, we would get r of 2 plus r of 1 and r of 2 minus r of 1. Next thing we're going to do is I'm going to multiply in a 2 so that I can divide by 2. And I'm doing that, as you'll see in a second, to kind of change this into some. So mathematically, this is still the same, because if I wanted, I could cancel these 2's out, and then we just have what we had in the step before. But I'm going to multiply a 2 here, so I can divide this by 2. All right, so what do we got now? Well, what we have is this new equation that we can use to do this. This r2 minus r1, that is represented by this change of r. That would be this distance right here. If we subtracted the two radiuses, the outer one and the inner one, that would give us that length right there. We're going to call that change in r. Our height is still our height. This 2 pi is still this 2 pi. The last thing in this is this r. And we get this r, we're going to call r the radius from the center to kind of the center of that shape. It's an average. And if the way you'd find it, if you add two things and divide by 2, you're finding the average. So this ends up being r, which is our average radius. So what we're going to do now is we're going to take that and find the integral of it. And why this is going to work is you can kind of think of this cylinder, if we were to take a scissor and say cut right along here somewhere and open this up and lay it flat, you would get this rectangular shape over here that has a little bit of width to it. And if you cut that open, this length from here to here, that's the distance around the circle. And the distance around a circle is called circumference, and we'd find that circumference by doing pi times diameter, or since we know diameter is equal to 2 radiuses, circumference would also be 2 pi r. So we're going to use 2 pi r to find our circumference. And circumference in this case, if we were to take a cut of this like we talked about before, that radius from here to here, that would just be the length x, because if we're picking a point on that, that would be the x value to that point. So our circumference ends up being 2 pi x. Okay. Our height, same thing here. Like if we have a point here, we talked about this distance would be x. Our height would be y, or another way of writing y in function notation would be f of x. And so the height of this is, our height is our function height to that point. And then the thickness of that, that's our change in, the thickness of this is our change in x, which is here, dx. So now if we were to repeat this same process with a bunch of shells, if you can imagine there's another one here that would create another kind of smaller cylinder in there, and we do it again, and there's another, and there's repeated cylinders. So we're doing all those cylinders from A to B. That would find this total volume of this whole shape. If you want a 3D kind of view of how this works, go when we're done here, there's a file in Schoology that'll bring you to a little video showing you more of a 3D look of this. So this is the shell's kind of equation that we're going to be using when we do the shell method. And it's going to be this 2 pi x is going to be in there for our circumference. Our function's going to change, so whatever the function height is, that's what we put in for f of x, and then dx. And then our limits would depend on where we're finding that from. So let's go back to that original problem and see if we can solve that out. So this one wants us to find what's this volume. So first thing, we're going to set up our limits, and it appears on this one that we're going to be integrating this from 0 to 2. Okay, next we got, if we had some kind of representative shape here, the distance from here to here would be x, and so our circumference here is going to be 2 pi x, because that would be our radius. Okay, next, what is the height here? Well, this height is just our function height here, so 2x squared minus x cubed. And then the thickness of that shell would be dx. If we integrate this now, this would give us our volume. All right, to solve this, it's usually easiest like we did with the disc and washer method. Take any constants, move those out. Once we do that, though, we still have this remaining x outside of this parentheses, and we can't integrate that x separately from these other ones. So that x is going to need to get distributed in order to get the function so we could integrate it. So now our volume function is going to look like this. We're going to take out that 2 pi until we multiply back later. If we distribute that x, what we're going to be integrating then is 2x cubed minus x to the 4th dx. Now we just go through and solve this like you have all these other integrals and go. So antiderivative here would end up being, got to go up a power to 4. Reciprocal's 1/4. 1/4 times 2 is going to be 2/4, or 1/2. This other one, we can go up to 1/5, or to 5, with a reciprocal of 1/5 in front. Integrate that from 2 to 0. If we plug in 2 here, 2 to the 4th power is 16. Half of 16 would be 8. If we plug in 2 to the next one, 2 to the 5th is 32. So we get 32/5. If we plug in 0, both of those end up being 0. So now just simplifying that out, 8 here is the same. If we get a common denominator, would be the same as 40/5 minus 32/5, which would be 8/5. So if we take now multiply back our 2 to that, that's going to make that 16/5 times our pi, and our exact volume then would be 16 pi over 5 and whatever these units are cubed. So that would be the volume. The shape this would create would kind of be like this. It almost looks like a bundt cake, where it's kind of hollow. It's got volume to it, but it kind of gets hollowed out almost in the middle a little bit. Again, there's a video on Schoology if you kind of want to see the 3D view of that. All right, let's see if we can kind of do this one a little bit better, or together a little bit, and see if you can set it up. So first, let's graph this one out. We have a parabola here. We have a straight line, another straight line. So let's put that on the graph and see what we got. So this parabola of x squared is going to start at the origin. And then like if you put 0 in, you're going to get 0 zeros right there. If you put 1 in, 1 squared is 1. Negative 1 squared is also 1. 2 squared is 4. Negative 2 squared is also 4. So looks something like that would be the parabola. Y equals 4, that's just a straight line, horizontal line here through 4. And then x equals 0 would be a vertical line, basically the y-axis right here. So the volume in between that, and this problem should have probably been a little bit more specific here. Usually what they talk about when they do these is they'll say like in the first quadrant or something. That really should be in this problem. But what we're looking at here is what are we going to get if we take this volume and rotate that around the y-axis. Okay, what are we going to get? So on this one, now we want to do the same thing. Think about like a representative rectangle here. And if we have that, what is the radius going to be? Well, the radius from here to here is just x. If it's from the y-axis, it's going to be x. So our volume is going to be 2 pi x. What's our function height? Well, this one, kind of going back to some of that stuff we did with area and some of the other volume problems you've been doing, there's 2 functions involved here. So if you got 2 functions involved, you want to use, kind of like we talked about before, to get that height, you want to subtract the 2 functions that are making up that height. So here, the function on top is y equals 4. The function that is on bottom of this is the parabola of x squared. And then the thickness would be dx. And we'd be integrating this from, it looks like for sure 0 here, to wherever this point would be. I think we can see that that's definitely 4. If it was a U of M test question, make sure you do show that the intersection point ends up being 4 there by setting the 2 points, oh, sorry, not 4, 2. Make sure you show that by setting these 2 equal and solving it. And what I mean by that, if you set these functions equal to see the intersection point, you can see very easily by taking the square root, you get plus or minus the square root of 4, which is plus or minus 2. Okay, so now why don't you pause the video and see if you can integrate that and see what you come up with. All right, let's just check quick. Make sure, like we talked about in the last one, you can pull the constant out. Make sure that x gets distributed. Find the antiderivative now of that new function, which ends up being that. If you plug in 2, you're going to get 8 for that first one, and then 2 to the 4th is 16. 1/4 of that would be 4. If you plug in 0, you're just getting 0 for both. Subtract that, you get 4 times the 2 pi, you end up getting 8 pi units cubed. And we've talked about you can definitely use calculator to double check that if it would be a test question. Just make sure you multiply by the 2 pi at the end. All right, let's try another one here. Find the volume of the solid obtained by rotating around the y-axis again, this region of y equals x, between y equals x and y equals x squared. All right, so let's graph that out. Y equals x, we know, is just this line, 45-degree line that's going to pass through the origin because we get points at 0, 0, 1, 1, 2, 2, negative 1, negative 1. So that would be y equals x. The line y equals x squared, that's that parabola we looked at before. There's going to be points here. And you're going to get this parabola shape. So that's the y equals x squared. So where's the area in between? Looks like we're looking at that little area right there. All right, so now, like we've been doing on these other ones, let's set it up. Volume equals, this one clearly we can see is from 0 to 1. We need our circumference. If we took a representative cut of that, the radius there is x, so we got 2 pi x. The height of that would be the function height. So we have to, looks like here, the height of that, you got to subtract those two. So it'd be the one on top, x, minus the one on bottom, x squared. And then our thickness would be dx. For this one, let's use the calculator, just kind of show that again, see what we get. I'm still going to pull that 2 pi out. And then distributing is not too hard. Let's just distribute that. So x squared minus x cubed dx. So let's use calculator. On this one, remember, you're going to want to hit your math. Find that integration one. Here we're going from 0 to 1. Type in our function here of x squared minus x to the 3rd power. And then get that x after for our dx. Whoop. Got that deleted there. There we go. All right, so now once you hit enter, you should get this. Again, as a fraction, we can hit our math and see what that is as an exact fraction, 1/12. Now, got to be careful here. You don't want to put 1/12 down as your answer because we still got that 2 pi there. And so the final answer would be 2/12, which is the same as 1/6 pi, or pi over 6 units. For these assignments, now that you've done a bunch of these, if you want to use your calculator to evaluate, I'm fine with that, but make sure come test time that you do want to make sure you show your work in there. But we've done a couple now where we've shown work, so just want to kind of review with calculator. All right, last one here. Find the region bounded by these functions, and then see what you get by rotating around the y-axis. Why don't you pause the video at this time, see if you can graph this one out first, and then hit play to kind of test to see if your graph looks correct. All right, let's see if your graph looks right here. Y equals 1, that's the horizontal line here just going through 1. X equals 1, that's a vertical line going through 1. And then this y equals 3 over x, you should have gotten kind of this line that kind of curves down from the top and bottom here. So the area in between, we're looking right here. So hopefully you got that when you graphed out. All right, next part. Again, pause the video and see if you can set up the integral that we would use to find this using shell method. All right, let's see how you did. If you took some representative rectangle here again, that radius is going to be the x value to that point, so you should have had x, 2 pi x here for our circumference. And then our the height of that would be the top minus the bottom. The top is 3 over x, the bottom would be 1, so subtract those here for our height, and then our thickness is dx. And you should have had that from 1 to 3 because you can see over here you got from 1 to 3 is where they're intersecting. All right, next, now see if you can pause the video and solve this one out and see what you get. All right, let's see how you evaluate it here. Again, we can pull our constant out of 2 pi here. Make sure you distribute that x. When you multiply that x to that first one, those two x's actually cancel out there, so you're just left with 3. And then x times 1 is x. Antiderivative shouldn't be too hard there. Plug in those numbers, and remember here you got to subtract them. One of ours isn't 0 here, so you got to find the values for both and subtract them. And if you keep going here and get common denominator, 9 would be the same as 18 halves minus 9 halves would be 9 halves. And then 3 minus a half is going to be 2 and a half, or 5 halves. Subtract these and you get 4 halves, and multiplying you're going to get 4 pi. And so you should have got 4 pi units cubed, hopefully. And again, you can double check with calculator. So that's finding this. Try those practice problems out.